So I'm going to give again my just a mini repeat of what I filled the last 5 minutes with, which is just to say thank you all of you for joining again for the training today. We are really grateful to have you. We see you as our partners in this development and know that we do, and call upon us to help you get even more out of this program and out of the capability of the IDAES system. That is our purpose. Certainly drop notes on me or emails or phone calls, voice, text. If there's anything that I can do to help connect you up with what you need in the program, certainly talk to anyone who's on the call today to help you move further along with your use of IDAES and your applications. Jaffer also mentioned that we have a group beyond the users group that's called the Stakeholder Group that meets once a month by phone, by conference call, and web meeting, and presents to you what new capabilities are being developed, tells you about the new releases, all that sort of thing. So if you want to get involved for an hour a month to keep up to date, you can certainly join our Stakeholder Group. And we will have face-to-face meetings once a year. Again, the next one is going to be the last week of October. Okay, so enough of an introduction from me. I'm going to turn the ball over to Andrew Lee. Andrew's one of our key development people, and he's going to lead you through the next step in your simulation work. So Andrew, take over.
Thank you, John. I probably should share my screen. Hopefully you can all see my screen now.
We can see Slack, Andrew.
Well, that's my screen. So,
yep.
Thank you all for attending. Is there a way I can stop seeing those? Maybe you can't. Anyway, so thank you everyone for attending today's tutorial. Hopefully most of you have been able to attend the others. Yesterday, Jaffa went through the basics of modeling unit operations in IDAES and things we can do with physical properties. And today we're going to go through how we take unit models and assemble them together into an actual flow sheet. So just as a reminder, I'll go through the process of actually opening up the Jupyter notebooks for everyone. I'll start an Anaconda prompt. So for those of you who went through and followed Keith's instructions, remember that if you created a Conda environment, you need to activate it. And then get to the directory where you installed or put your examples. Mine are in a slightly unusual place because I'm working off a development branch. And what did I type wrong? It worked every other time I did this. Examples dev. There we go. And then start the notebook by typing Jupyter notebook. Hopefully that's the worst of the issues I run into today. So open up the index notebook, and today we are going to be looking at module 2, where we'll simulate an HDA process and do some optimization. So, as I said, today we're going to go through how we assemble a flow sheet, and then simulate that flow sheet and do some optimization. So the problem we're going to look at today is the hydrodealkylation of toluene to form benzene. So this reaction here, where we have toluene plus hydrogen gas reacting to form benzene and methane as a byproduct. So the flow Somebody muted me for some reason.
Sorry about that. Missed a click there, Andrew.
So hopefully I caught that before I said too much without being heard. So this is our process here, where we have a stream of hydrogen with a small methane impurity, plus a stream of toluene being mixed together. We send that to a preheater, then to a reactor, where our reaction will occur. Then we send the products to a flash drum, where we'll separate the liquid phase products, the benzene and toluene, from the light gases, hydrogen and methane, hopefully with a minimum amount of loss of the products, the liquids out the top. We'll then purge some of the light gases and recirculate the rest back so that we're not wasting hydrogen. And the liquids will then separate into benzene and toluene. Normally we'd use a distillation column to do this, but to keep things simple and manageable for this workshop, we're just going to use a single flash drum. So the split's not going to be very good, but it's something that we can solve fairly easily. So to begin setting up this flow sheet, the first thing we always need to do is import the various bits and pieces that we're going to use. So for those of you who were with us yesterday, you'll be familiar with some of these: constraints, variables, and concrete models. But today we're also going to see some other Pyomo components such as expressions, objective functions, and the transformation factory. And we're also going to make use of the Pyomo network toolbox, which is what we use to connect individual unit models together into a flow sheet and then help us initialize that set of interconnected units. So if we just execute this cell, so that's imported all the background things. The next thing we need is the flow sheet block from IDAES that we'll use to assemble our flow sheet. And then we need to import the various unit models. So we've got 6 different units that are going to be part of this process. The mixer, heater. For the reactor, we're just going to use a stoichiometric reactor to keep things simple. Flash drum, a separator, which in IDAES we're going to use which is our splitter, and a pressure changer on the recycle stream just to make sure that the system remains at constant pressure. So we can import all of these from the IDAES generic model library. So from IDAES.genericmodels.unit models, we can import pressure changer, mixer. We're going to import the separator, but in this case, we're going to give it the name splitter because that's what it's behaving as. Heater and stoichiometric reactor. So make sure you execute the cells if you're following along. Of course, if you note, I haven't imported the flash drum yet, so that's a task for you to do. So from IDAES.genericmodels.unit models import flash, and then Shift Enter to execute. Before I forget, if the screen looks a little bit small for any of you, up in your top menu bar, there's some view options, which has a zoom control that you can use to zoom in and out. So we're also going to import some utility methods to help us with looking at our flow sheet. From those of you who were yesterday will recognize the degrees of freedom tool, which we use to see how many degrees of freedom are in our model. But we're also going to import this thermodynamic assumption component. I just remembered there is a bug in this line. This should be from IDAES.genericmodels.unitmodels.pressure changer. Now, because there are many ways you can model a pressure changer, isentropic, polytropic, simpler ideal versions, this is how we tell the default IDAES pressure changer model which of these assumptions to use. And you'll see that later when we actually create the pressure changer in the flow sheet. So just pause here quickly to make sure nobody's had a problem up to this stage and make sure you got that correction to the line of code right. I'll take that as a good sign. So that's all our unit models imported. The next thing we need to do is the properties that we're going to use for this system. So we've provided the thermodynamic property packages that we're going to use for this so that we don't have to create them. So we're going to import the HDI ideal VLE package as our thermodynamic properties. However, this process also has reactions. So in addition to just the thermophysical properties, we also need to import a reaction package which describes the reactions that will take place. Because we're doing a very simple stoichiometric reactor in this case, our reaction properties are very simple. They just describe the stoichiometry of the reaction and the heat of reaction. And we'll use this when we create the reactor later on. And this will automatically set up the reactions for us so that we don't have to do anything. So we can just import that cell. So that's all the importing out of the way. Now we actually get to the fun part of actually building the flow sheet. So the first part of any IDAES model is we need to create a concrete model that will be the foundation of everything. And then we add a flow sheet block to it. Again, we're only looking at steady state models at this point, so we set dynamic is false. And this will create a steady state flow sheet in the background that will be the canvas on which we build the process. So now that we've got a flow sheet, the next step is we need to set up the properties within that flow sheet. So again, unlike module 1, we've got both the thermodynamic properties, which those of you who were here yesterday will probably recognize this line. So in my flow sheet m.fs, I create an object called thermoparams, which is an instance of the thermodynamic property package that we imported. However, I also need to set up the reaction parameters in much the same way, except in this case, every reaction parameter block must be linked to a thermodynamic property block. This is because reactions are fundamentally dependent on the thermodynamics behind them. And so this primarily serves as a check to make sure things don't get cross-wired later, and that if you're doing a more complicated process where you've got potentially multiple thermodynamic property packages in the system, that you don't accidentally use the wrong thermodynamic property package with a reaction package. So when I add the reaction package, I have to set a property package argument and point it at the thermodynamic property package that I just created. So now we've got the properties done. The next step is to start adding unit models. So before we get into all of this, I should note that the IDAES unit model library was built to be flexible. So it's got the ability, it's got a lot of, every model has a number of optional arguments or options that you can set. For example, the mixer, you have the ability to tell it how many inlets there need to be and what those inlets need to be named. Now, the list is fairly long and there's no way for me to go through them all, but I will point out that all of this is available in our documentation, for which there is a link here that points you directly to the IDAES unit model library, where you can see all the core IDAES models, and that documentation will list the options available, what they mean, and how you can set them. So let's start from the beginning of our process and add the mixer. So I'm going to call my mixer M101. So on my flow sheet, m.fs, I add an object called M101, which is an instance of the mixer. And I need to provide it at least two arguments. The first one is I need to link it to the property package we're using. So property package is m.fs.thermoparams, the object we created in the last step. And then I need to tell the mixer how many inlets it should have. In this case, I'm telling the mixer not just how many inlets, but I'm telling it that I want them named toluene feed, hydrogen feed, and vapor recycle. So when this mixer is created, it will have 3 inlets with those names. Can then also add the heater. So in this case, again, we need to link the property package. And then I'm saying for this heater, there's going to be no pressure drop across the system, the unit. It's going to be isobaric. But because I'm dealing with a system that has potentially 2 phases, I want it to calculate phase equilibrium at the outlet, just in case I cross the 2-phase threshold.
So can IDAES handle different property packages in the same flow sheet? And is there any limitation to that in terms of which ones mix with which?
You can have as many property packages you want. Basically, any single stream will have a single property package associated with it. So, but for example, if you've got a heat exchanger where you've got 2 separate flows on each side could have a different property package. And we also have the ability that if, for example, you want one property package for the first half of the flow sheet and a different property package for the second half, because one part you want to keep really simple, the other you want rigorous detail, or the state changes sufficiently that you need different sets of parameters. We also have what we call translator blocks, which basically just represent a node in the flow sheet where you change the property package for a given stream. So,
okay, so
stream
you do
coming
have
in
to
has one property package, the one going out has a different one. Beyond that, you can have as many as you want in a flow sheet, with the only caveat being that you have to keep them organized in your head, and they do take up a little bit of memory. So the more you add, the more complicated the problem becomes.
Okay, thanks.
So next, we're going to add the stoichiometric reactor to the process. And this is an activity for you to do. We're going to create reactor, calling it R101. So to the flow sheet, I add an object R101. It's going to be an instance of stoichiometric reactor. Then I need to give it these options listed above. So to give a model some options, we start by setting default is equal to what we call a Python dictionary. So curly braces. They don't show up too well in the Zoom, but these are braces, not parentheses or square brackets. And then I can set each of the options listed above. So firstly, property package is equal to is m.fs.thermoparams. Next, I need to set the reaction package as well, because this is our reactor. It needs to know what the stoichiometry is, and potentially in more detailed reactors, what the reaction rate expression looks like. So I do that by setting the reaction package option, and pointing it to the reaction parameter object we created earlier. And then for this reactor, I wanted to include heat of reaction, because we want to know how much the temperature is going to change. Well, the enthalpy is going to change due to the reactions going on. So I'm going to set that option to true. Just as a passing note, you don't have to use heat of reaction for these processes. It is also possible to implicitly include the heat of reaction in your actual enthalpy calculations. We leave it up to the user to how they want to do it, because different options may be better in different circumstances. I also want to have heat transfer in the reactor. So I'm going to say has heat transfer is true. So because we've got a heater reaction, we're also going to allow for a cooling duty in the reactor. And then finally, I don't want to worry about pressure change. Change, not kahang. So I'm going to set that option to false. And assuming I typed everything correctly.
Misspelled transfer. Heat has heat transfer.
Yep. Which I should have known because I always mistype transfer. I also misspelled stoichiometric. What have I done here? Pressure change. Oh, so many typos. And
you might need to.
well, technically I don't, but I'm going to do it anyway. You can actually ignore that warning in most cases, but to make sure everything runs cleanly, I'm going to clear all my output and then cell run all above and wait for it to catch up. And now we're good. So I'll just stop to make sure that everybody's keeping up at this point and see if there's any people having trouble. I'll take that as a good sign and assume you all type better than I do then. Oh, no, there's something in chat. Anything important, Jaffa?
No, you can
Okay.
move along because I think they were pointing to the previous typo in your Stoic reactor.
Thank you. I knew I was going to mistype at least one thing going through this. So now we've added the code for all the other unit operations for you, so we can just execute these cells. If you want to look through, you can see the different options we set for some of these units. Probably the one that I should mention is the pressure changer. So you'll remember I mentioned that thermodynamic assumption earlier. So when we created the pressure changer, we had to set a thermodynamic assumption to tell the model what sort of calculation it should use for work. Because we're doing a really simple problem, we've used a trivial isothermal compressor. So this doesn't really represent any real compressor, but it keeps the calculation simple for the example. So this is the option you'd use if you're not really worried too much about rigor at this point, but just want to get something up and running, or if you're maybe doing a conceptual design where energy doesn't matter too much. So now we have a flow sheet with all the units on it, but we haven't told the model how these units are connected together. So the next step is to describe the connectivity, and we do that using arcs, which come from the PyMO network toolbox. Basically, an arc is just an object which describes the linkage, and it says that a port in one unit is linked to a port in a different unit, or more simply, actually, two ports are connected. So we've got an example here in the next cell where I'm creating an object which I'm calling S3 for stream 3, which is the stream between the mixer and the heater in my very poorly labeled flow diagram. And here I create an arc and I tell it that the source of the arc is the outlet of the mixer and its destination is the inlet of the heater. That's all it takes to describe this stream here.
So what are the mechanics of that? Is it like literally linked, you know, the way Python can link objects? They're the same object now, or are they just, there's a method in place now to pass the information between the two or something?
So we'll actually get to that in a couple of lines. At this point, this is just an abstract description that says to PyMO that there is a linkage between these two ports that we're going to have to do something with later. Okay. So once we create all the arcs, I'll actually show you the next step. So the next one is I'll get you to create. So we're going to create stream 4, which links the heater to the reactor. So we create an object called S04, which is going to be equal to an arc. The source is equal to m.fs.h101, the heater, dot outlet. The destination is going to be m.fs.r101 dot inlet. So that creates the arc linking these two. We've filled in all the other ones for you, but just a few things to note as we go through. For example, our first flash drum has 2 outlets. So rather than just outlet, we have to say VAP outlet, and later on there will be a lick outlet, so vapor and liquid outlets. And if we look at the mixer, you can see here when we connect the recycle stream back, we're saying that the vapor recycle stream, which is the name that I gave for that stream back when I created the mixer. So as was just commented, what do these arcs mean? So at this point, arcs are just an abstract description. Just to diverge a little bit into some Pyomo, Pyomo works on the concept of describe the model in the form that's most natural to the modeler. So much like basically the equations as we would write them on a sheet of paper, and then later transform that description into a form that the model, that a solver will actually understand. So for this case, we've just described an abstract linkage that this port is linked to a second port. That doesn't actually mean anything to a solver. So now we are going to apply this network.expand-arcs transformation, and we'll apply it to the entire model. So what this does is it goes and looks at every arc and sees this abstract description, and then it writes a set of equality constraints that take the variables in the outlet of the first unit and writes an equality that says they must be equal to the inlet of the second unit.
Hey, Andrew?
Yep.
Can I pause you for a bit? We had a question in the chat. One of the users had a problem with they're getting the name error, like name flash is not defined. So I guess that, so if we had to import the flash, that was the only unit that we had to import.
Yeah.
So a couple of questions. If you added that line of code,
and make sure
for
you
the import,
executed that line.
and then if you executed that line.
Yeah, so that's all the way back up here.
I had that issue as well. Just make sure to use a capital F there.
Yeah, when it comes to the actual objects that you're importing out of the library, they will almost always start with a capital F or a capital letter. That's, we've used standard Python naming practices for everything. So these things are classes, and they will always start with a capital letter. So did that resolve the problem?
Yeah, I hope so. If all the other imports work, then you have the right environment on. So I don't think that's the issue. Yeah, it helped. Yeah.
Okay.
Thanks, Andrew.
So just make sure they've caught up to where we are.
So with the arcs, can Pyomo/IDAES handle bidirectional flow, for example? Is it just, I mean, source and destination, is that like it has to go from one to the other in one direction, or is that just a naming convention?
It is primarily a naming convention within IDAES.
Okay.
It does primarily indicate, within IDAES, it basically indicates the direction of expected flow. But because underlying they are an equality constraint, it is possible for the flow to go negative as long as when you define flow rate in the property package, you allow for a negative flow.
There's a place to allow it, whether it's negative?
So this basically goes, flow within IDAES is contained within the state blocks. We basically treat it as a state variable. Normally, we like to think of state variables as just being intensive, but in order to give this modular framework and the flexibility we wanted, we actually include extensive flow information in that. So when we declare the state variables, one of which will be flow, or some of which will be flow, we can also set a bound on the flow. So a lot of cases we'd say, well, flow can never be less than 0. If we did that, then reversible flow would not be possible. But if we think that reversible flow could happen, then we would allow for a negative flow rate in the process. And then, yes, you can get bidirectional flow.
And is there a default? And I'm asking because like for some of our models, we purposefully have bidirectional flow. It's like for energy storage systems, you got to go both ways.
Yeah.
So that's why I'm keen on this.
So there's not really a default in that sense. It is something that you set when you create the property package or set it up. So with the current system in IDAES, you basically have to write your property packages yourself, in which case you have full control over those bounds. In the next release, we actually have a framework for making that easier. And again, it provides an interface for setting those bounds. So there is no default. It is entirely in your hands.
Okay.
It's up to you to choose.
Andrew.
Yep.
Although the arcs technically allow that, most of the unit models would not be happy with a negative flow rate. Correct?
You sure? I think most of them would actually, the unit models themselves shouldn't mind, most of them.
Okay. Just double checking.
Yeah. In most cases, it should not matter. The one thing that would you might have a little bit of a problem with is pressure change across units, in that if flow reverses, the pressure change should also reverse, but which you'd need to take care of in the model. But other than that, I think it should be fine. Was there some other comment?
I have a question. When you're connecting two units, the property of the strings are also connected implicitly?
Yep.
Okay.
So when we create the arcs, it is actually checking to make sure that the inlet and outlet are compatible.
Okay.
So PyMO makes sure that you don't accidentally try to link two ports that use different state variables. But yes, the idea is that the inlet and the outlet should be using the same thermodynamic property package. And if you come to a point where you want to change property package on a given stream, we've got the translator blocks I mentioned earlier, which is basically a block which says the inlet uses this property package, the outlet uses a different property package, and then you, the user, have to come in and provide a mapping between the states at the inlet and outlet.
Okay, thanks.
So any more questions at this point? Okay, so I just executed this arc transformation and we didn't see any messages, so it worked properly. So now the flow sheet actually has the connectivity described in it in a way that the solver will understand. So the next thing I'm going to show is adding some extra expressions to the process, the flow sheet. So for example, when we're doing a process like this, one of the things we're generally interested in is the purity of our product stream, which is not explicitly described in any of the unit models. So what I'm going to do is I'm going to create a PyMO expression, which I'm going to attach to my flow sheet, that calculates the purity so that I can easily look at it and say, is that purity sufficient? So the way I do it is I create an object attached to the flow sheet called purity, and I'm going to use this PyMO expression component. And in the expression, I can provide it with just a mathematical expression describing the quantity I want. So in this case, purity is the amount of benzene in the vapor outlet of my second flash unit, divided by the amount of benzene and toluene in that stream. So something that I should have mentioned earlier, but I forgot to, is in this property package we're using, we're actually describing the state using molar flow rates of each phase component pair. So we actually have 8 flow rates in the process. Benzene in the vapor phase, benzene in the liquid phase, toluene in the vapor phase, toluene in the liquid phase, etc. The reason I'm doing this is primarily to show that IDAES can do this. You have flexibility over what your state variables are going to be and how you describe them. And this is to give you the ability to pick or try to find the most tractable form when you're dealing with more complicated problems. It's not the most obvious set of state variables to use, but it can have advantages in some cases. One of the big ones in this case is because my state is actually described by phase and component, the flash information is already in there. So I don't have to do a separate flash calculation at the inlet of each unit to work out the phase partitioning. So one other comment that I'll make at this point is just the IDAES standard when it comes to indexing variables. The order of the indexes will always be time first, then phase if appropriate, then component if appropriate. They will always be in that order. So that just helps us when we come to naming because we know exactly which order to put things in. So if I execute this cell, so this has now created that expression on the flow sheet. Expressions are sort of, in the simplest explanation, they're halfway between a variable and a constraint. They're not actually seen by the solver and solved directly, but they are something that I can evaluate and get a number for when I've solved my model. So later on, I'll be able to say m.fs.purity.display, and I'll be able to see the actual numerical value of this expression. Just for later purposes, we're going to do an optimization. So I'm also going to add some expressions here for operating costs. So a cooling cost being based on the heat duties of the first flash unit in the reactor where we're doing cooling. And similarly, a heating duty expression for the heater and the second flash where we'll be heating. And then I'm going to create an overall operating cost expression so that later on we can see what's the operating cost of this process and we can then optimize for cost. So that's basically described all the things I want in the flow sheet. Next thing I need to do is actually look at my degrees of freedom and see how many things do I need to fix before I can try to solve this. So if I use the degrees of freedom tool, it shows me that I have 29 degrees of freedom, which is quite a few. However, each of our feed streams has 10 degrees of freedom, 8 flow rates, temperature, and pressure. So between the 2 feed streams, the toluene and the hydrogen, that covers 20 of these degrees of freedom. So here I'm going to set the conditions for the toluene feed. If I were to refer back to the top, I'd notice that my specification for this stream was 0.3 moles per second of toluene, which I'm going to put in the liquid phase, and nothing else. However, zeros in flow rates often result in nasty problems with the solver. You can get singularities or degeneracies. So rather than setting these to 0, I'm actually going to fix them to a small positive number. Small enough that it won't affect my results, but also large enough that it avoids any singularities I might run into. Then I'll set the pressure and the temperature at my inlet conditions. Similarly, I'll do the hydrogen feed with the numbers just above there. So that sets all my feed conditions. So I should only have 9 degrees of freedom left, which will be the operating conditions of the different units in the process. So first one, in the first unit, the heater, I'm going to fix the outlet temperature at this point. The next unit is the stoichiometric reactor. So my specification for this is I want 75% conversion of the incoming toluene. Now, stoichiometric reactor doesn't actually know what conversion is, because conversion has to be based on some reference component. And because this is a general model, we don't know what, it doesn't know a priori what the reference component might be. So we have to add that constraint ourselves. So I'm going to add a variable for conversion, which I'll initialize to 75%. I'll also set a lower bound of 0 and an upper bound of 1. And then I'm going to create a constraint for conversion, which says that the conversion variable I just created multiplied by the inlet flow rate of toluene must equal the difference between the inlet and outlet of toluene. So the normal conversion equation, but I've just rearranged it to take the normal division by the feed rate and put that as a multiplication on the left-hand side. I'll then fix my conversion to 75%, and I'll also fix the heat duty of the reactor to 0 for now, so no cooling. Just quickly pause to make sure there aren't any questions at this point or problems. And also make sure I'm not going too fast. I'll take that as no problems. So for the first flash drum, I'm going to set conditions of an operating temperature of 325. So I want to keep this cool, so as much of the benzene and toluene as liquid as possible. And I'm going to say there's no pressure drop change in this flash drum. So the next is a user exercise. We need to set the operating conditions for the second flash unit. So setting an operating temperature of 375 Kelvin and a delta P of minus 200,000 pascals. So set the temperature, I go to m.fs.f102, my flash unit. I'm going to set the temperature of the vapor outlet, which should be the same as the liquid outlet. So I could set either. Being equation oriented, it doesn't really matter which one we set. The equation, the matrix ends up being the same. And then I say temperature. I'll make sure I spell it correctly because I always mistype it too. And then fix is 375. And then I want to set the delta P of the flash drum. So m.fs.f102.delta P. So delta P is a variable in the flash drum itself, not in one of the outlets. And I will fix it to negative 200,000. And finally, I need to set the split fraction at the purge and the outlet pressure of the compressor, which I'm just going to set equal to the feed pressure to make sure that the pressure in the recycle loop is closed. And we can now check the degrees of freedom. And it is 0 as expected. So I'll pause here and make sure everybody gets to that point and that they see 0 degrees of freedom.
Quick question, when you call that degrees of freedom, will that tell you if you've overconstrained your problem as well?
It will tell you exactly how many degrees of freedom there are. So if you see a negative number, the problem's overconstrained.
Great,
If you see a positive number, it's underconstrained. So basically all it's doing is it's going through the entire model, counting the number of free variables and the number of constraints and getting the difference for you. Number of equality constraints. It is smart enough to identify, to exclude any inequality constraints that might be in there. So not hearing anybody with more questions or trouble, so hopefully you're all up to this point. So,
hey, Andrew,
yep.
one second. We had one comment in the chat window that one of the users is saying 50 degrees of freedom. So is this towards the end as well? Like this is at this stage?
How many degrees of freedom did we see?
Yes, I get 50 as degree of freedom.
50, 50.
Yes,
It's possible that you could have. It's possible you could have added a unit repeatedly, like there was some repetition with the unit, because the original problem had 29 degrees of freedom. So my guess is that you added another unit that you didn't intend to. It could be that flash. Did you add like or something else?
Yeah, that one's going to be, first thing I would do is clear the, so kernel, restart, clear all output, then come down to here where you were and run all cells above, then execute the cell and see if you still get 50.
Okay, I will.
So Andrew, Rob also had a good comment in the chat window that the degrees of freedom does not detect linearly dependent or otherwise redundant equality constraints. That's for the user too.
Yeah.
Yeah. So that was a good point. Just wanted to point that out.
Yeah. Unfortunately, we can't easily detect degeneracies and things like that. Much like Aspen Custom Modeler and similar tools. You can have a model that is theoretically 0 degrees of freedom, but is still degenerate or poorly posed and may or may not solve. How are we going with the degrees of freedom problem?
I haven't heard or got any feedback on the chat window.
But I have another. I did it. I click on register and clear output, and I run the parent degree of freedom. Give me an error. Name degrees of freedom is not defined.
You would need to also do run all above first.
Yeah. So once you have done the restart and clear output, so whichever, like let's say you were on the degrees of freedom cell, click on that cell and then go to that toolbar that Andrew is showing right now and run all above. So it will run all the cells above, because what's happening is that you need to run the cells above for those libraries to load. And that's why you're seeing that error right now.
It's okay, thank you.
Okay. So now we've got everything defined. We've got a square problem. The next thing we need to do is initialize the problem. Now, initialization of equation-oriented models is not an easy task. However, we can actually do this in a sequential modular fashion, much like tools like Aspen Plus run, where we solve each model in sequence, starting with the beginning, where everything's defined, solve this unit, and then take the outlet values, pass them to the next unit, and solve each of them in order. However, we have a recycle loop in this process, which makes things a bit more complicated. The process simulator tools have inbuilt functions that will determine a tear stream for this, which is they'll identify a stream and say, if you can provide me initial guess for this, I can then iterate sequentially around the cycle and eventually close this to the solution. And the Pymo network toolbox has a similar tool, which we're going to use here. So we start by creating this sequential decomposition object, which we imported way back at the beginning from the Pymo network toolbox. And we can set some options for this. So it's got a few ways of identifying the tear stream. There's heuristic type methods, which are similar to what the process simulators use. But because we're also in an equation-oriented environment, there's an option to use a rigorous mixed integer approach to identify the minimum number of tear streams for the process. That, however, requires a mixed integer solver. And because we don't have one for this demonstration, we want to keep things simple, we're just going to use heuristic methods. There's also different methods for how we'll go about converging the tear stream. We're going to use Weggstein acceleration, which should help us close the stream faster. However, I'm also going to set a limit on how many times it can iterate to close this tear stream to 5. Now, that is almost guaranteed not to close the tear stream, but that doesn't matter because once we just need to get this close enough that our final nonlinear solver can actually take over and finish the job. So to execute this cell quickly, just to demonstrate how it works, I'm going to actually break this down a bit. So I've set it up so it will report to us the tear stream that it identifies and the order that it will iterate in. So if I look at this next cell, it will tell me which stream it identified as the tear, which was stream 3, between the mixer and the heater, which makes sense. We need to tear this recycle stream once. Some of us might have decided to tear after the reactor, given that we might know more about the state there. But in this case, it picked between the mixer and the heater, which is good enough for this problem. We can also look at the order it's selected that it will solve things in. So it's obviously starting from the tear stream, solving the heater, the reactor, the flash, separator, the compressor, and the mixer, and then iterating in that order to try to converge this tear stream. You'll note that our second flash is not part of this order because it's outside this loop and it will be solved at the end. So here's what it's identified. So in order to do this sequential approach, we have to first come up with a guess for the state of this stream. We're going to go with the simple guess of, let's assume that the recycle stream's negligible, and we'll just use the sum of the inlet streams. So we've gone and added them all up here, picked the inlet conditions of the two. So I just create a dictionary describing that set of tear guesses. And then to the sequential decomposition tool, I use the set guesses for function, and I set the inlet of the heater to the tear guesses. The next thing I need to do is tell the sequential decomposition tool what it needs to do for each unit to initialize it. So as we saw yesterday, every IDAES model has an initialize function. So all I have to do is set up a function that will call that. And then I tell the sequential modular tool to just run using the function I defined. And this will take a little bit of time because it's now going through and sequentially solving everything. So whilst you're waiting, just watch the star here. Because whilst it's a star, it says it's still running. And then when it becomes a number, it means it's finished. So there's a whole lot of output here because it was reporting to me what was going on. But the important bit is at the end, it's telling me it found an optimal solution. So that probably means everything ran properly. Just one other thing that I'll show in amongst this large wall of text is this line here where it says, warning, Weggstein failed to converge in 5 iterations. So as I said, we set a limit on how many times it can iterate the test stream, and it wasn't enough. But it will have been enough that we can solve the entire problem. So obviously the next step is to actually solve the problem. So we create a solver. In this case, we're using IPOpt. And then we say results equals solver dot solve m. So we apply it to our model. And I'm going to set t equals true. T equals true just tells the solver to print your solver output to the screen so I can see what you did. And so I get these results. I'll check my number of variables and number of constraints to confirm that yes, it was a square problem. I see that it took 9 iterations to solve. Just in passing, you will frequently see this message come up. You can ignore it for at least square problems. We've spoken to the IPOpt developers about it, and they've said, yes, we know about that. And at the end, optimal solution found, so our flow sheet solved. And hopefully your flow sheet solved as well. So now let's have a look at some results. So we added an operating cost expression before. So let's actually print the value of that operating cost and see how much the yearly cost is. So it's costing about $420,000 a year. It's a somewhat arbitrary number because we just picked some arbitrary cooling costs. But later on, we'll try to minimize this cost whilst meeting some requirements.
Interestingly, I got a different answer. Is that because of some randomness in the way the optimizer works, or I have different inputs somehow?
You probably have a different input somewhere. So, yeah.
Also, did the solver converge? Do you see optimal solution?
Yes,
Yeah.
I do.
And no degrees of freedom, like square problem.
Yeah. Check these
My
two
window's
numbers.
so
should be
tight.
the
Hold
same.
on, let me see. Yes.
Interesting. That probably means that somewhere you put in a different number for one of the fixed variables.
Yeah, maybe I just have a typo somewhere.
Hopefully it's not a problem going on, but well, you got an answer.
Yeah, I did.
Okay,
Actually,
if that number is different, it could just, how off are you?
It's 387,000 instead of 419.
Okay.
Yeah, chances are it probably doesn't matter in the end because when we do the optimization, we're going to unfix just about all those variables anyway. So hopefully the next bit will look the same.
Something is not 419.
Sounds like someone else got 387 as well.
Interesting. You should be getting the same answer as me. So as long as you each got an optimal solution found though and had a square problem, I think we'll just move on for now. The numbers themselves don't matter too much. It's the process, hopefully, that I'm demonstrating. Any complaints to that?
Nope.
Okay. So next thing we'd like to look at is, let's have a look at what our product streams were. So I'm going to use the report function for our flash drum, the second flash drum, which will show me what the inlet and outlet streams of that drum were. And I'm also going to print the value of the purity expression we created earlier. So for those who had different numbers before, you'll probably get different numbers here. So I'm getting about 82% benzene purity, which is pretty good considering I've got a single flash drum doing this separation. If we look here, the vapor outlet is our benzene product. So I'm getting 0.14 moles per second of benzene, small amount of toluene. But there's a bit of benzene going out in the liquid outlet as well, but that's because we're using a single flash drum. So that's how we can look at the results of a single unit. But when we're talking about flow sheets, often what we'd like to see is a summary of at least the key streams. So for that, we use a stream table. So IDAES has some tools for building stream tables, which we can import from the tables utility methods, which is IDAES core util tables. So we can create a stream table data frame, and then we have a method that will convert that data frame into an actual readable string that we can print. So first I'll create the data frame, which I'm just going to call ST for now. So create stream table data frame, and then I tell it the streams that I want to see. You can provide an arc or a port on a unit, whichever you feel like. So in this case, it's already set up to show the stream leaving the reactor, which is stream 5. And I want to have a look at the light gases stream leaving our first flash drum to see what's actually going out into the purge and recycle. And I happen to know that that is stream 6. So I'm going to add to my data table here a label called light gases and link it to m.fs.s06, the stream, and then print that stream table. And we get something that looks like this. So the big thing to note here is,
Hey, Andrew.
Yep.
We had 2 users say that they got the similar numbers that you got. So the score is 2-2 right now, and the mystery remains. So
yeah,
but a few of them are getting that number. So
yeah, well, we'll see. We might look into it later. So the big thing to notice here is that, okay, out of my reactor, I'm getting 0.35 moles of benzene. So that's nice, that's my product. But almost 0.15 moles of that is actually going out with the light gases in the first flash drum, which means that some of it's being purged and the rest is being recycled, rather than going to our product as we'd like. So turns out that's actually about 42% of our product. So it's fairly obvious that we can do better, or we hope we can do better. So let's try to optimize the process to minimize this loss and reduce our operating cost. There's also an optional cell here if you want to try and look at additional variables or streams in the process, but in the interest of time, I'm just going to keep going. So how do we optimize our process? Well, the first thing we're going to need is an objective function. So I'm going to add an objective to my flow sheet using the Playamo objective object. And the thing I want to optimize is the operating cost. So I set the expression equal to the operating cost. And by default, Playamo assumes that the objective should be minimized unless you tell it otherwise. The story I hear is that operations people are all pessimists, so minimization is the default. So I'll add my objective function. Next, so that in order to optimize, we need to have some degrees of freedom in the problem. So I'm going to have to go and unfix some of the variables that are fixed. So I do that by, just like before I said whatever the variable was dot fix, now I just say dot unfix. And that will release the variable so that it can be solved by our optimizer. And we've got a user exercise here for you to unfix the remaining variable, which is the pressure drop in F102. So m.fs.f102.delta p.unfix. So that's unfixed all the variables. So this is why I said, hopefully, if you made a mistake in putting a value in before, it doesn't matter because we just unfixed them all anyway, and we'll let the solver try to optimize them. However, unfixed variables generally should be bounded so that the problem doesn't wander off into infeasible territory. So we're going to add some bounds to each of these. So just like fix and unfix, variables have a method called setLB and setUB for bounds. You'll note, those who are being attentive here will note that there's actually a time index here on temperature. This is actually because last time we ran this workshop, set LB and set UB had to be applied to individual variables at a point in time. We've since actually fixed that in PyMO, so I don't think the time index is necessary anymore. And you can just fix a variable all at once. But this is how I set the bounds on a variable. So we're being asked here to set the bounds on the reactor 1 outlet temperature.
You didn't run that cell.
Oh, thank you. That's actually the important one because that's the bound that's going to matter later. I'm going to see if I'm actually right about having fixed this. I'm not going to put in the time index. If I look up above here, my bounds are 600 and 800. And I'm going to do this quickly. And it works. So yes, we fixed that underlying issue in PyMO. And we've set all the other bounds for you because that would be tedious otherwise. So that's given some degrees of freedom, but this would let the model do just find the minimum cost, which would primarily be don't do anything. So we need to add a few final constraints to say that there's a minimum product flow rate we need to create, and there's a minimum purity. I think there's a third constraint I add somewhere. Yeah, and we also want to limit the amount of benzene that's going out in the overhead of the first flash drum. So that's the first constraint I'll write. I'm going to create something called overhead loss on the flow sheet, make it a constraint. Now I'm going to say that the flow rate of benzene in the vapor outlet must be less than or equal to 20% of the total benzene leaving the reactor unit. So in other words, no more than 20% of my benzene can go to the light gases stream. Next, we need to add a constraint for the flow rate of benzene in the product stream. And we're going to set a minimum flow rate of 0.15 moles per second. So we need to add the expression here. So we do it by starting with expr. So this is telling the constraint, this is the expression you're to work with. Now I want to say that 0.15 must be less than or equal to the flow rate of benzene in the vapor outlet of F102. So it's m.fs.f102.vap outlet dot flow mole phase comp time 0 vapor phase benzene. And I'll pause there to make sure everybody gets that right.
So we had a question. This is, I think, primarily for either John Cirola or if Michael Bynum, if anyone can answer. Question is it possible to perform optimization by connecting a IDAES model to Dakota optimization toolkit from Sandia National Labs?
I am not sure. I think I don't know a lot about Dakota, unfortunately. So if
all right,
John might be able to type in, but I think Dakota. Yeah, I can't say for certain. Sorry.
Okay. Ashish, thanks for asking that question. We will get back to you via email, with the answer for that question. Thank you.
Any other questions or problems at this point? Okay, so I'll move on. We've got a constraint here that says the purity of our product stream must be greater than 80%. This expression is really easy because we've already created purity before in the flow sheet. And now to solve the optimization problem, all we need to do is run the solver again. So those of you who had the same result as me before should see something like this. There are a total of 343 variables, but only 338 constraints now, because now we've added some degrees of freedom. My solver takes 22 iterations to solve this problem, and it finds an optimal solution. Hopefully those of you who had a different answer before also see something similar and get an optimal solution. So to finish up, let's see what this actually did. So for me, running this optimization, my operating cost is now down to $312,000 a year. So that's about $100,000 a year cheaper from memory. So we've made the process a lot cheaper. But did we meet our constraints? Well, the benzene purity is 82%, about what it was before. So we're meeting our 80% purity requirement. And we're also producing the 0.15 moles per second of benzene that we were required. Obviously, it's sitting on that lower bound because doing anything more is more expensive, and we just said minimize the cost. If we go look at our overhead loss out of F101, now we're seeing that the benzene flow rate there is much smaller, so we're losing a lot less benzene in the process. And we can have a look at what the solver found as the optimal values for each of our variables. So for the heater outlet temperature, it said 500 Kelvin, which happens to be our lower bound. And this actually makes sense. Our reactor is a stoichiometric reactor. It doesn't actually matter what temperature it's at. So there's actually no incentive to preheat the product. Thus, the heater temperature is sitting on the lower bound. The reactor, we can see, is heated up because of the heat duty, the heat of reaction. But the other thing we can see here is that probably the other one of interest is our final flash drum is operating at the lowest possible temperature, again, pressure. Again, this makes sense because this is the easiest separation, makes the separation easier. It's actually operating fairly close to the lower bound of temperature, but in this case, it's being limited by the operating pressure. And so that is the end of module 2. Hopefully you all got through and at least got some answers out at the end. Hopefully you even got the same answers as me. So I think at this point we stop and ask for questions. We do have a quick demonstration to follow this of some new tools that are coming up in the next release. So we should leave 5 to 10 minutes for that, but I think we have some time.
Hi, can you hear me?
Yep.
Hi, so the question I have is related to the model library of IDAES, and that is basically like, is it possible to make unit models such as a filter press, or for example, rotary drum filter, something like that?
Yes, it is. So first comments to make is that the IDAES framework as a whole is completely open. So it is designed such that if there is something missing from the libraries that you need, or the models don't quite fit the need, what you'd like them to do, you can go in and build your own easily.
Okay.
There are a lot of unit models that aren't there yet. We are gradually expanding the model library. I don't think filter presses, etc., are particularly high on our list just yet, because we're driven primarily by projects that we're working on. We use these tools ourselves. But yeah, the tools are built so that to try and make it as easy as possible for you to add new models into the framework. And I will say that if you do develop some of your own, we would love to have them back, have them ourselves to add to our models. And this is an open source project, so we
Right.
do appreciate contributions.
Okay, sounds good. Thank you.
So Andrew, if you can stop sharing and then pass the ball to Michaela. And in the meantime, we have one more question. This is a good question. Which equation of state is used in this example? That's the first part. The second part is that if they wish to use a Peng-Robinson equation of state for the current example, what would they have to do? They are saying that they will bring the parameters needed. So you want to take that?
Yep. So this model was just ideal gas with Raoult's law. It was deliberately kept simple to make it something we could easily do. But yes, you could do it with a cubic equation of state. There is currently a general cubic equation of state property package in IDAES that you can build off. It provides the foundation of the core equations. Primarily, all you need to do is come along and provide the constants, the parameters for the species. So you can write up your own property package that derives from our core cubic class and just add in the parameters and a few other things that you'll need, listing what the components are. I will say, again, that in the next release of IDAES, there will be a new interface for the property packages that makes this a lot easier. The cubic equations of state are actually sitting on my computer right now in the final stages of validation. So once that is released, it will be even easier, and all you'll need to do is pick from a library of different methods for the pure property components, provide a set of parameters, and away you go. I also noted in our chat window that it seems John Sorolla made an answer about the coda.
So, yep. So I think that answered Ashish's question, and I think that's all the questions we have. So, Michaela, good to go.
Thanks. So my name is Michaela Shepard, and I work at Lawrence Berkeley National Lab, and I'm going to show you an upcoming visualization tool that we're adding to IDAES in the next release. And this is still in active development, so there are some things that will change, but the actual calling of the function will not. So you guys aren't going to be able to follow along because this is not a part of IDAES yet. But you would do m.fs.visualize, and then you give the model a name. And when you run this, it will hopefully pop up a web page. If it does not pop up a web page, the other thing to do would be to take this URL and then put it into your browser. So it popped up a visualization of the model that we just used. And you're able to move things, you're able to move the labels, and you're able to show and hide the ARC labels. And then one thing you're allowed to do is, let's say you want to change the model, you want to solve, change things and then solve the model, in which case right here, I'm just going to add a flash and an ARC. And you run that, and then you would run visualize again with the same name. It'll pop up a new web page, but now it has your changes right here, and it preserved the layout. And you're also allowed to save it, and there's help as well. The look of this is going to change very soon, but again, as I said, this is an active development.
So this saved in this kernel or whatever, but I assume when you rerun, you would have to redrag everything?
Yes, that is why we have a save function. So it will actually save it to a file, and then you're able to share that file, or you can reload that file and it will reload the visualization. Any other questions or comments? I'm happy to have comments. Okay, thank you.
So that, or I guess I have, so that will be available as soon as you do the arcs and whatever that other function is that combines them or whatever, I assume?
Yeah, yeah. So basically what I did was I just added the arg in that the arc in the Flash, and once I added that and then I did the visualize again, as soon as it pops up that a new window, you have the changes in that new window. Thank you.
So we had a question.
Yeah, sorry about that. I just wanted to say that the visualization tool is quite impressive, and it sort of helps to make people, like a generalized public, to know how the basically things going to look like. So yeah, that's quite impressive.
Thank you.
Thank you. So we have one more question as to when the recording will be available online. We will have it. We will all. I will already be posting the one from yesterday, so that will be available today. But the one from today will be available by close of business tomorrow. So it should be available soon, and we'll send an email out as well. So if there are no other questions, John, any closing comments?
Yes, first, thank you to everyone for joining in again today, and thank you for all the active questioning interactions. You know, that's a very important part of what we're doing here, is giving you the opportunity to interact with us, and we benefit from all the questions that you ask and all the little errors that happen in operating the system. As you see, we're not immune to those either, so not to worry about that. But I think very importantly, we also want to get your recommendations as to what directions you'd like us to go in that would make these tools more usable for you, and provide the kind of capabilities that you need to have. So please don't be shy at all about making recommendations to us about how you plan to use the tools, or things that we can do to make everything more usable. That's the end of my comments. We're really glad to have you as our partners in this development, and please do continue to interact with us. Anything else to add, Jeff or Andrew?
Nothing from us. Thank you all for your interest, and you know, we look forward to hearing any suggestions or comments. And if there's anything that you think that we can help you out with, if you're trying to use IDAES in your organization, please reach out and we'll be happy to help.
All right, everyone. Thank you for joining our community, and I believe this concludes our call for today. All the best, everyone. Stay healthy.
Thank you.